Hey guys, in this section we're going to take a look at the orbit and rotation of Jupiter. Jupiter takes pretty near 12 years to go around the Sun. Technically it's 11.88 years, but good enough for government work is 12 years. So what you're looking at here is a picture, and I'm afraid I can't tell you who was taking these pictures, but every year, not necessarily from the same place on Earth as the person moved around, I believe, and not necessarily with the same photographic equipment either. The person took pictures of Jupiter over one full cycle, over one Jupiter year. And you can check those out. They're just stunning pictures. The detail there is really, really nice. Certainly superior to anything you would see in a common telescope. I think you'd need a pretty big telescope to be able to see that kind of color and detail. So, Jupiter is the fifth planet from the Sun, sandwiched between Mars and Saturn. There really ought to be one more planet right here between Mars and Jupiter, but Jupiter's immense gravity field prevented that planet from forming. And so instead of a planet, we now find an asteroid field. I should look up what the total mass of those asteroids would be. Another thing to keep in mind is that Jupiter took a lot of asteroids, a lot of debris, if you will, in the solar system, and either chucked it out of the solar system with its gravity or chucked it into the solar, put it into highly elliptical orbits that resulted in these asteroids either leaving the solar system altogether or crashing into something in the inner solar system. This happened a long time ago. It's generally associated with the late heavy bombardment that happened ended about 3.8 billion years ago. Jupiter is just about straight up and down. The only planet you can see with a smaller tilt is Mercury, and what this means is that Jupiter gets heated pretty evenly over the course of its orbit. As opposed to that are planets like Earth and Mars that have this significant tilt. That results in seasons. So, for example, in the northern hemisphere, when we are tilted towards the sun, we call that summer. And then on the opposite side of the sun, when we're tilted away from the sun, we call that winter. Jupiter doesn't have anything like that. You'll also notice that Venus is rotating in the opposite direction of just about every other planet. That's called retrograde motion. And Uranus has an interesting kind of motion. It's rolling, so to speak, as it orbits the sun in such a way that its south pole is always pointed towards the sun and the north pole is always pointed away from the sun. That's unique in our solar system. Okay, so Jupiter is going around the sun once every 12 years, but how long does it take Jupiter to spin on its own axis? In other words, how long is a day on Jupiter? Here you can see for Earth, a day lasts about 24 hours. On Mars, it's a little closer to 25 hours. On Jupiter, a day is 10 hours. That is really quite something if you consider that Jupiter is much, much larger than Earth or Mars. It's spinning really, really fast. And that's one of the reasons that the planet is slightly flattened. The faster things spin, the more they tend to flatten out. Saturn's in the same boat, so the two biggest planets in our solar system are both spinning very, very quickly, and then you can see the ice giants are sort of in between those two. Measuring Jupiter's revolution or rotation is very difficult to do. We do it with radio waves, but before I get into that, let's just take a look at this for a moment. What happens is that the clouds at Jupiter's center are rotating faster. The clouds that are in the temperate zones, north or south, are rotating slightly more slowly, and the clouds up at the North Pole aren't rotating very quickly at all. What this means is that if you're going to talk about Jupiter's rotation based on something you see on the planet's surface, you have to say where that object is. So if you're going to talk about Jupiter's rotation in terms of the Great Red Spot, that's going to be close to an equatorial zone. And astronomers have decided to call that System 1. If you're going to talk about Jupiter's rotation based on something like these smaller white storms down here, that's in a temperate zone. That's something that astronomers call System 2. And then much, much more difficult to observe, partly because of the color and partly because of it's just sort of out of our field of view, are the polar regions, and those are called System 3. And so for a long time, if you talked about Jupiter's rotation, you'd have to talk about, are you referring to System 1, System 2, or System 3? And what astronomers decided is they wanted something that everybody could agree on. They wanted to measure the rotation of something that didn't depend on the cloud tops necessarily. And that worked out to be this. Jupiter has a tremendous magnetosphere. You may recall that Jupiter's magnetic field is pumped up by its interaction with Io. Jupiter's gravity squeezes Io, making the moon extremely volcanic, easily the most volcanic object in our solar system. And when these volcanoes on Io erupt, they send particles hundreds of miles into space, and some of those particles are ionized. In other words, they become charged particles, and that's what this red donut is. This red disk, or torus, is called the Ioplasma torus. And the effect of that is to make Jupiter's field very large. It's like an amplifier for a magnetic field. These blue lines are Jupiter's magnetic field lines. And what people said is, why don't we follow these magnetic field lines as they orbit? Because they co-rotate with Jupiter. If Jupiter rotates once, all the magnetic field lines rotate once. So why don't we use that instead of cloud tops, right? Because these things they're all coming out of the North Pole and entering the South Pole. So how fast they're rotating has nothing to do with the cloud tops of the planet. Well, it turns out you can do that because Jupiter's magnetosphere generates radio waves. And so if you're sitting on Earth, or if you've got a satellite near Jupiter, and you can record these radio waves and measure them, and you can figure out how they're related to Jupiter's magnetic rotation, you can work backwards and establish a day on Jupiter, how long it takes to rotate once. This picture is showing aurora on Jupiter's northern cloud top, I believe, the North Pole. And a couple of things that are interesting here. One is this bright spot, and then there's a bright spot here and another bright spot here. And what those are footprints left by electrical currents generated between Jupiter and 3 of its Galilean moons. This bright spot is left by Io. These spots are left by Europa and Ganymede. You say, well, what's that all about? What happens as Io rotates, it establishes a current. It turns out that Io does not rotate at the same rate as these magnetic field lines, which means Io is cutting across these magnetic field lines. And if you were taking physics, you'd find out that anytime you have charged particles crossing field lines, that's going to generate current, right? And so you get this current. It's almost like a circuit between Jupiter and Io. And where that electrical current, blammo, hits the North Pole of Jupiter, it lights up. The electricity lights up the atmosphere, just the way electricity in one of the overhead lights in the school, a phosphorescent light at school, lights up. And then the same thing happens to a lesser extent with Io and also with Ganymede. These are just aurora, right? These just represent charged particles that aren't associated with any moon smacking into Jupiter's northern cloud tops. And so that's Jupiter's rotation and orbit.